Ideal gases can be thought of fluids made up of tiny little particles or atoms. Each of these atoms has a kinetic energy and they're bouncing off of the wall, off of each other in a completely random pattern, kind of like what you see here. Notice how some of the particles are moving slow, some of the particles are moving fast. This is a completely random motion of each of these particles. They are bouncing off of each other and they are bouncing off of their container. Now what we can do with our sample is make a histogram of each of the particles' kinetic energies. Now some of the particles will be on the lower end of the spectrum and have a very low kinetic energy, while some will be on the higher end and have a high kinetic energy. Some of the particles will be meh and have an average kinetic energy. The majority of these particles will have this kinetic energy given to you as 3/2 kBt. T is temperature and Kb is Boltzmann's constant. Now we can also get the velocity from this, or the root mean square speed. This is not the average speed, but this is the speed of the particle with that average kinetic energy. Let's say I have two containers that I'm going to fill with the same amount of gas. Now, one container obviously has lower volume than the other, but each has the same amount of gas. Now, each container is experiencing a force from those particles bouncing around against them. That force is from the pressure, which is given as pascals, which is 1 Newton per square meter. Now, if I decrease the volume, I'm going to up the intensity of those collisions and therefore up the pressure. Also, if I add heat to a container, I'm going to also increase the pressure, because we saw that kinetic energy was dependent upon temperature. If I increase the temperature, I increase the kinetic energy, therefore experiencing more force. Kind of like what you see here. My pressure is holding pretty steady right now. I have a solid container and the particles are bouncing off the walls. You can also notice that some of the particles move very slow in the simulation while others move extremely fast, taking us back to that histogram I drew. Now, if I have this little man here push the sliding door forward, I'm going to lower the volume of this container. There is less room for the particles to bounce around. Notice what happens to the speed of the particles as I move this container closer to the other side. More particles are moving faster than before. There is a greater average kinetic energy than before. Because of this, there is more impact force experienced by the container walls. Because of that, there is more pressure. The area of the walls didn't change. Therefore, there is more force being exerted against the container walls. This also happens if I add heat. Ooh, fire. If I add heat to the container, my temperature is now at 780 Kelvin, and now look how fast the particles are moving. I add more heat, and my pressure goes up. This also happens if I add more particles. Whoa, pressure went up a whole lot there. This leads us to the ideal gas law, PV equals nRT, or PV equals capital N kBt. Lowercase n is number of moles, capital N is the number of particles, R is 8.31 joules per mole Kelvin, temperature is always in Kelvin, and Kb is Boltzmann's constant. Now, you may be wondering to yourself, how do the units work out on this? I've got pascals times meters cubed equals moles over joules per mole Kelvin, yada yada. I can get the other side to joules, but then I've got Pascal times meters cubed. Pascals are pressure, which is force over area, newtons per square meter. Let's plug that in and see what we get. Newton meters equals joules. Now you may be wondering, how do Newton meters equal joules? I'll give you a second. Work is force times distance. Haha. Force is newtons, distance is meters. Work is in joules, therefore Newton meters have to be joules. It works. That's the joke, see, because it works.